Almost all of us are stuck in a crisis and wondering what to do next in a perplexed situation like this. Let's understand how situations are tackled when a disease spread. Hello friends, I am Khalid. Welcome to my YouTube channel Bioblogger, and today we are going to talk about the SIR model of contagious diseases. So without any further ado, let's jump into this. You may ask that more than 2 months have passed since the spread of this disease. So why am I making this video now? But wait, this is just an end to the lockdown and not to the pandemic. We have got a bigger responsibility in front of all of us. Talking about the SIR model, it is one of the most basic models to understand the dynamic of a contagious disease. I am calling it a very basic model because there are many modifications to it, and also there are many other models as well. But I'll try my best to stick to this one only. Just a quick disclaimer, I'm not an epidemiologist, not a mathematician as well. So I won't be focusing much upon the equations and their derivations. But what's most important for all of us is the inference that we are going to draw from this model. The story of this model begins in 1927 with the theory of Kermack and McKendrick. This theory was published in the Proceedings of Royal Society, and it was based upon the work of Ronald Ross and Hilda Hudson. Ronald Ross was a very famous personality. He was the first British Nobel laureate. He won the Nobel Prize of Physiology and Medicine in 1902 for his work on transmission of malaria. In this model, we classify people in three different categories. First one being the susceptibles. These are those people who are prone to get infected. Second one is the category of infected people itself who are spreading the diseases. And third one is the removed category, which have moved out of these two categories and either get recovered or died. Here in front of you are the differential equation that is denoting the change in number of individuals in each category that we discussed earlier. Now, before coming to this, we have to assume a few things, and it totally makes sense because it is not an easy task to determine the variation and dynamics of any complicated disease with some simple mathematical equations. For that purpose, we have to turn a few things in our favor, and it is done by making a few assumptions. So our first assumption will be that the disease is spread for a very short period of time and the factors like birth rate and death rate are negligible. So our first assumption can be that the population size is going to be constant throughout the spread of the disease. Our second assumption will be based on the fact that any contagious disease spread only when at least two of the people come in contact with each other. And who are these two people? At least one of them should be from the susceptibles category and one of them should be from the infective category. Even if someone from removed category come in contact with these people, the disease is not going to be transmitted as they are immune to the disease. So our second assumption will be that the disease or the transmission of the disease is going to happen only when there is communication between them. So the transmission of disease is proportional to the contact between the susceptibles and infective. Our third assumption will be that the rate of recovery is going to be constant throughout the spread of the disease. And why so? Because all the infectives are treated alike, and it makes sense that everybody is alike. So everybody is treating alike and everybody is recovering or dying with same pace. Now, as you can see that there are two transitions, one from the susceptibles to the infective category and second is one from the infective to the removed category. So the rate with which there will be decrease in the number of susceptibles will be the rate with which there will be the increase in the number of infective, and this makes sense because people coming out of this category are going into this category, and the rate with which the susceptibles are decreasing is given by a rate constant A and the product of infectives and susceptibles, their total number. And why there is a negative signs? This makes sense because the number of susceptibles is going to decrease no matter what, but if the disease is spreading, the number of susceptibles is going to decrease throughout the spread of the disease. Before coming to the second equation, let's see the third equation first, which is the rate of recovery or the number of individuals removed from these two categories, the rate of removal of individuals from these two categories, and it is given by the recovery rate or the removal rate B and the number of infectives. So the product will be a gain in this category. So now it is simple to calculate the number of infectives because it is given by the di by dt is denoted by AIS, which is the loss from this category, and what is subtracted here is the gain in this category. So it is very simple. Just keep in mind that A is the transmission rate and B is the recovery rate. All these equations make much more sense when we look at its graphical representation. So what I have done here is I've plotted a graph of total individuals or the population versus time on x-axis. Now let's look at each equation one by one and try to understand how number of individuals in each category are going to change as the time progresses. First, let's look at the number of susceptibles. So it is going to change at the rate of minus AIS. At time t equals to 0, the number of susceptibles will be the maximum. It is denoted here by S initial, and at any point of time during the progression of disease, S initial is going to be greater than number of susceptibles at that point. And as the time progresses, the number of susceptibles is going to decline at a rate which is given by AIS and up to the end of pandemic. Now, at the suppose this point to be the end of pandemic, and at this point minimum number of susceptibles will be left. Coming to the second equation, the number of infectives. At time t equals to 0, number of infectives will be very few. But as the time progresses, there will be contact between the S and the I, that is the susceptibles and infectives, and at a point, and the number of infectives will increase. But at a point when there will be not enough susceptibles left, or there will be very few susceptibles, the number of infectives will start declining and ultimately it is going to reach 0. Coming to the third equation, the number of removed persons from these two categories are going to change. It is totally dependent on the number of infectives, and there is no role of susceptibles in this. So as the number of infected will increase, the number of removed will also increase. But even if when the number of infectives are decreasing, the number of removed persons are increasing, and it will show an exponential growth. Now I am going to introduce two new terms in front of you, and probably the two most important terms to understand the impact of this model. First one is denoted by Q, which is the contact ratio, and it is calculated by the ratio A, which comes from this equation, to B, that is the recovery rate, or precisely the removal rate. Now, what does Q mean? This is a very important statement, that Q is the fraction of population that is going to come in contact with the infected people. I am repeating it. Q is the fraction of population that is going to come in contact with the infected people. Why is Q so important? And the answer to this can be understood in the next term, and the term is R naught. This is not a new term. You would have heard it many times in the past 2-3 months. And what does it mean? This is the basic reproductive rate. It represents the secondary infections from an already infected person, or in other words, how many individuals can get infected from a diseased person. Getting my point? I hope this is making some sense. R naught is calculated by Q times the initial number of susceptibles. Now again, I'm not going into derivations, but one thing that we can conclude from this equation is R naught is directly proportional to Q. Think it this way: can we change the number of susceptibles at any point of time? And the answer to this is no. The only way to keep R naught in check is to keep Q in check. And how to do that? You all know the answer really well. Maintain social distancing, wash hands, keep proper sanitization, stay at home, etc. By doing this, what are we doing is we are actually trying to decrease the Q, which is ultimately going to decrease the R naught value of this disease. R naught is one of the most major problems in the present scenario of COVID-19. There are diseases like seasonal flu which have R naught value of about 1 to 2. There is MERS and SARS which have R naught value lesser than 1. But on the other hand, we have COVID-19 that is probably having the R naught value of 2 to 6. Now don't get confused when I say that this is not the highest value of R naught you are going to see in all the diseases. There are diseases which have R naught value of more than 6, but the problem with this disease is unfortunately we don't have any vaccine to this right now. On the other hand, there are diseases like Ebola, measles having R naught value but much higher than this, but fortunately we have cure to them. Before coming to an end, let's have a look at what inferences we can draw from whatever we have studied in the SIR model. First and the foremost, can we call all the contagious diseases epidemic? And the answer to this is no, we cannot. Why? Because only those diseases which have R naught value greater than 1 can be called epidemic. There are diseases which have R naught values lesser than 1. They are contagious, but they cannot be called epidemic. Of course, there are more factors as well, but for this instance, let's keep it here only. Secondly, what is the best way to understand the impact of a pandemic or an epidemic disease? Simply look at what is the total number of persons that got affected with that disease from a population, and in the end of the pandemic, what is the total number of susceptibles that are left unaffected. So we are going to look at them one by one, and fortunately we can get to know both of them by the help of SIR model. Firstly, I would like to draw your attention to this equation. Now don't be afraid, this is a very complicated equation. We are not going into derivations or the details of this equation. Simply have a look at what this equation represents. It is giving the idea of total number of people getting infected with the disease throughout the course of its spread, and it is given by initial value of the infectives plus initial value of the susceptibles minus some constant. What is that constant? I'm not going into the details. Before going to plot a graph for this equation, I just want you all to know one thing, that this initial number of infective plus initial number of susceptible represent the total population. How? Remember in the beginning that I said that in SIR model we categorize the population into 3 categories, S, I and R. Now if you think that what will be the number of removed person from the category from the removed category at time t equals to 0, and the answer is 0, because there will be no one recovered or died at time t equals to 0. So the total population will be represented by infectives and susceptibles, and this is what I am going to say here. Now if we look at the graph here, this constant, if we consider it as a function of Q, I have plotted a graph here of the function of Q versus Q. So when we have a larger Q, as the Q is increasing, this function of Q is decreasing. What I want to say is that for a larger number of Q, we have a very small number of f of q, the function of q. What does that mean? That we have a very small number of this value to be subtracted from the total population, and the smaller this number of the value, the larger will be the number of people getting infected with the disease. I hope you are getting my point. Secondly, have a look at this graph again. This represents the total number of susceptibles remain unaffected at the end of the pandemic, and again it is given by equation, but I'm not going into the details again. Just have a look. The number of susceptibles remain unaffected is versus q graph. If I plot, as the number of q is increasing, as the value of q is increasing, this number is decreasing very steeply. So this is really haunting that one thing, only q, is affecting so many things and so harshly. In the end, I just want to talk about one thing. As you all know that we are moving out of the lockdown now, and by that I simply mean that we are going to increase the contact ratio, that is Q. Basically, there are many possibilities to what can happen next, and based on your understanding, you can believe in whatever possibility you want to. Are we heading towards the herd immunity approach? What is herd immunity? I'll talk about it later sometime. But the big question is, how are we going to flatten the curve when we are going to increase the contact ratio? Because these are the two contradictory things. If you take my opinion, until and unless you believe in the medical facilities of your country blindly, don't even dare to increase the queue by coming in contact with each other. Maintain social distancing, wash your hands properly. That's it for this video. Let me know if you liked my work. Subscribe to this channel for more informative videos like this. Share this video to spread my words, and comment section is open for any query or suggestion. Catch you guys in the next one. Bye bye.